Hi, this is Professor Fernandez. This is video 1 in lesson 15. We're talking in this video about applied optimization problems, and actually we'll be doing that in the other 2 videos in this lesson as well. So I'm going to go through applied example 4.23 from Calculus Simplified. So this is an example, as we just talked about with the topic heading, of using the optimization theory that we learned in the lesson 14 videos and applying it to some real world examples. So the first thing I would say there is that check out video 14.2 for a review of that optimization theory. What we're going to use, for example, are notions of critical numbers, critical points, first derivative test, maybe things like that. So check out that video for a review. Over here on the right hand side, you'll notice 2 big boxes. I'm really only going to use this box. Oops, sorry. Only going to use this box for this particular example in this video. What are these 2 boxes? So I'll zoom in a little bit here. This box that I circled is how to find the absolute extremum or extrema of a continuous function defined on a closed interval. We'll see in this example in a minute that that's exactly what's going on. You see that there's 3 steps here. The first is find the critical numbers on the interior of the interval, in other words, exclude the endpoints. Calculate the critical values. Remember, that's when you substitute those critical numbers into the function to get the y values. And then also calculate the y values at the endpoints. And then number 3, compare those numbers. The absolute maximum is the largest of those numbers, and the absolute minimum is the smallest. This is the procedure we're going to use in this example because, as you'll see in a minute, the information that we're given basically gives us everything we need for that procedure I just talked about. So what is this other box up here? Well, this is, if you'll notice, I'll zoom back in here, this is box over here, down here, 4.4. This is box 4.5, right? So this one comes after the one I just discussed. And this box is something that I'll talk more about in the next videos. This is a longer procedure for solving an optimization problem, again with a closed interval. The reason it's longer is because in here I am assuming that you are not given what we're going to call the objective function, the function you want to extremize, maximize, or minimize. And I'm going to also assume in this box here that you're given very little information. So you might have to, for example, draw a diagram. You might have to look for keywords to come up with the objective function. Right? So in more advanced optimization problems, this is the procedure that I'm going to suggest, and we'll talk about that again in the next couple of videos in this lesson. So let's go back to the example 4.23 on the left here, and let's talk about what's going on there. I'm going to speed things up a little bit, so I'm going to zoom in, and by speed things up, I mean you can certainly pause this video and read through the prompt yourself. I won't read through it because that'll just add a couple of minutes to the video length. What I'll do is I'll just highlight what we need to do, right? So down here, find the absolute maximum of V of R. So that's, again, one of the reasons why this is a simpler optimization problem. We know what we're supposed to do, okay? But really what makes it simple is we're given the function we want to, in this case, maximize. So this function is called, therefore, the objective function. Our objective is to maximize it specifically. And we're also given the interval. Okay, and this is a closed interval because it includes the endpoints. Okay, and then there's another thing we have to do. So it says then, given that experiments show that R is approximately 2/3 R sub 0, interpret this R value. So again, if you haven't paused the video or haven't yet read through the prompts, you might be wondering, what is R? What is V? Where's the, a real world application here? And long story short, this function is modeling the velocity V of air rushing through the trachea during a cough. So that's what V of R is modeling. And R is the radius of the trachea. So we're modeling the tracheal tube here as a cylinder. So we got this little cylinder. We imagine that your throat is a cylinder. Clearly it's not, but it's a mathematical model. And then the radius of your trachea is R. And then we have, when you're coughing, we have some air that's being expelled, right, going out this way to expel whatever is in your lungs or whatever might be trapped in your trachea. So that's kind of the real world context here. Mathematically, as I said, this box over here is the one we're going to use because we have our objective function, we have our closed interval, and we want to find the absolute maximum of it. So scrolling to the right here, we have a nice procedure. We want to find the absolute maximum of a continuous function. We'll talk about that in a minute, defined in a closed interval. So step number one, we're going to find the critical numbers in that interval. Okay, continuous function. All right, so now let's remove all this clutter and let's look at our objective function v of r and then talk about the type of function it is. So v of r over here, k here we're told is a constant, that's positive. R sub 0 is also another positive constant, the original radius of the tracheal tube. Before it changes, right, when you cough, that's what part of the problem is asking you to investigate. You know, that eventually the radius is going to contract, right, 2/3, less than 1, of its original size. So that's kind of one of the takeaways of the problem. So if you then go back to this function v of r, what's really going on is that this is a constant, and then r is the variable. So this function is basically a cubic polynomial, right? If we write it over here, k times r sub 0 minus r times r squared, and we multiply things out, right? Then we have k r0 r squared minus k r0 r cubed. So I just distributed this r squared in there. So, you know, you can see that this product here, k times r sub 0, is a constant. So this is like some number times r squared. And then this is the same number over here, minus a times r cubed. So v of r is a cubic function, cubic polynomial. Great, so we have some information about what v of r is, and we know it's a polynomial. We know that polynomials are continuous. So if I go back to my box here, I certainly am trying to find the absolute maximum, in this case, of a continuous function. And the interval is closed, so going back up here, right, we can write down next to this function the interval that our maximization is supposed to investigate. Our max problem is supposed to investigate, and that's the interval we get over here. So r is less than or equal to r sub 0 over 2, and less than or equal to, r is bigger than or equal to r sub 0 over 2, and less than or equal to r sub 0. This is the maximum that we are allowing in this model, the trachea to enlarge to, the original radius of the tube. And this is the smallest that we are allowing it to contract to. Okay, so now that we've discussed all of what these things mean, right, we are now squarely in math land. By that I mean we have a function, a continuous function defined on a closed interval. So we're going to go off and apply this procedure and find the actual maximum of this function. So first step, find the critical numbers. So I'll do that over here. What does that entail? Well, I have to find the derivative. And I'm going to go back to, let's go back to this form up here. So I'll find the derivative there. Remember, this is a constant, so I get 2 times that constant times r, differentiating r squared. And then over here I get differentiating r cubed, right, times r squared. Great, so I found the derivative. Now what's next? Well, so I want to find the critical numbers. Remember, that is where the derivative is equal to 0 or does not exist. Okay, there are no x values, or in this case r values, where the derivative does not exist because it's a polynomial. But there may be values where it's equal to 0. So let's try that. So one of the nice things about doing this on the iPad, I can just erase, and there we go. Let's set this equal to 0. If I do that, I can move things around. Equals 3k r0 r squared. And then I can remember that the k and r0 are constants, and they are positive. So I can divide through by those, get rid of them. There we go. And I can also remember that if I solve this equation, I could cancel out an r. I have to worry, can r be equal to 0? In this case, it can't, because remember, this is the interval for the r values, just like up here, that we're considering. So we are pretty far away from r equals 0. Remember, r sub 0 is positive, the smallest that r can be is a positive number divided by 2. That is bigger than 0. So I'm going to safely cancel out one of the r's, and that leaves me with 2 equals 3r. So r equals 2/3. Great. So r equals 2/3 is the r value that I have that I can try to look at the critical number. That's the critical number that I get. Okay, so at this point I would like to calculate what the value of the function is at this critical number. That's the second step over here. Calculate the associated critical values and also calculate the value of the function at the endpoints. So this is my critical number, and then I'm going to go back and erase these things and calculate my y values. You might be wondering, how do I know that this number over here is inside this interval? So there's one little piece of information now, again, that the problem gives us. So supposing r0 equals 1 centimeter. Aha. So I'm going to go back here and update what our interval is. Wherever I see an r sub 0, I'm going to put a 1. Okay. So our interval for r is really 1/2 to 1. And it doesn't affect the function that we just differentiated. R sub 0 is just 1. So it kind of doesn't appear here anyway. All of the algebra that we did still works out. And so the question is this critical number in the interval? And the answer is yes. It is between 1/2 and 1. If it weren't, by the way, then you would throw it out, right? We do not want to continue in this procedure with a critical number that is outside the interval, right? Because that is not the interval of interest. Great, so we have our critical number, and then step number 2, I'm going to find the critical value. So I'm just going to move this up over here, and then erase this part here. So find the critical value. So I'm going to take the function v and substitute in 2/3 and see what I get. So if I go back up here, and now I'm assuming that r sub 0 is 1 minus r times r squared. The r sub 0 equals 1 comes from here. Okay, then I'm plugging in 2/3 into here for r. So I get k times 1 minus 2/3 times 2/3 squared. Okay, so we can do all the math here. This is 1/3, this is 4/9 times k, so I get 4k over 27. So that's v of 2/3. That is the critical value, right? The y value associated with the critical number, this one, r equals 2/3. So now let's compare that to the y value associated with the endpoints. So remember the endpoints were 1/2 and 1 because r sub 0 is 1. So v of 1/2 and v of 1, we're going to calculate those. The easiest one is v of 1 because if I substitute r equals 1 in here, that term is 0. Okay, so v of 1 is 0. V of 1/2, if I put 1/2 in here, then I get 1 minus 1/2, that's 1/2, times 1/2 squared, that's 1/4, half times 1/4, that's 1/8, times k, so that's k over 8. So now what I want to do, because I'm looking for the absolute maximum, we are now in step 3 of this procedure. What is step 3? I will compare the largest, or I will compare these 3 numbers, these 3 y values, find the largest, because I'm looking for the absolute maximum. Okay, so remember k is positive. So both this number down here, and this one are positive. This is 0, so this is not my maximum. It must be one of these two. How do I determine that? Well, you can just calculate 4/27 and 1/8, or you can use any technique you want to realize that 4/27 is bigger than 1/8, right? So this ends up being, therefore, the largest y value, and hence it's the absolute maximum of the function v of r. So I should say in a moment, we have found the absolute maximum, right? And we have to go back to the question and determine exactly what it is that they wanted us to supplement that with, or to how they wanted us to express it. Find the absolute maximum. Okay, great. We have that information here. This is the absolute maximum value, and it occurs when r equals 2/3. And then there was, remember, that second part. Given that experiments show that r is approximately 2/3 r0 during a cough, interpret this r value in the context of your answer. Great. So we would say, hey, in this case, r sub 0 was 1 centimeter. And the maximum, the r value that produces the maximum v of r value, we just derive to be 2/3. 2/3 times 1, right? Which is like 2/3 times r sub 0 when r sub 0 is 1. So one thing we can say then is that it appears that what nature is doing, if this mathematical model is fairly accurate, which it is, can be in many instances, it appears what nature is doing then is that it is contracting your trachea to 2/3 of its original radius. Again, we're assuming it's a cylinder. It's a big assumption. For what purpose? Well, to maximize the velocity of airflow through the trachea. So that's pretty cool, right? So your body apparently, in many instances, is trying to help you out. If you're coughing, you're trying to expel something from your lungs or your trachea. And certainly the fastest velocity of air that your body can muster will help you get whatever you need to get out. So that's pretty interesting. And again, this is something that comes out of some mathematical modeling and a lot of calculus, like we've shown. Okay, so let me go back and talk about something that I mentioned a minute ago, and then I'll recap in the video. The way that the procedure we used in this video to find the absolute maximum came from this box 4.4 that I keep talking about over here on the right-hand side. This is not the only way that you can find an absolute maximum, either theoretically, meaning devoid of a real-world context, or in the context of a real-world problem like this one. There are other procedures, right? So in this course, this is the procedure that I will most often allude to because it is a fairly mechanistic, right? So there are 3 steps, and that's always nice when you know what to do and when you're done. But again, there are other ways you could have done this. So what's another way? You could have used the first derivative test and found that this function, because it only has one critical number in the interval that we are looking at, this function seems to be increasing before that critical number, 2/3 for r, right? V prime would be positive before then, and then negative after that. And then you could argue, for example, that on this interval, which is all we care about, the function basically increases and then decreases. So this point must be a local maximum. So you could use the first derivative test to conclude it's a local maximum. Then you could say, hey, it is the only place where this function has a zero slope. So you could investigate the endpoints and then say the y value at the endpoints is lower than the y value here. So in other words, that gives you this kind of pseudo picture. It's not exactly a downwards opening parabola, but gives you the intuition that these y values are lower than that one. So yes, not only is that a local maximum, but because of all this information, you can conclude it's a global maximum or an absolute maximum, as we're looking for in this problem. So long story short, there are other procedures you may have seen out there. You may see in a different textbook. There is also this procedure. So this is not the only way then to find absolute maximum values and apply that to real world context. So last thing I'll mention for this example, in the next couple of videos in this lesson, as I mentioned at the beginning of this video, we will talk more about this box 4.5 all the way on the right hand side. Give you a little tip. When you are doing these optimization problems, they will take a while. Certainly, this is a lot of text here to read. And there is a context here that's real-world context. In this case, air rushing through the trachea. A lot of times, that context is, in some sense, superfluous to the mathematics. So as we kind of did here, you can find the absolute maximum using established procedures in theory that we've talked about in this course, not needing to know anything about the physiology of the human body, right? On the other hand, right, and this is part of what we'll say about this box in the next couple of videos, if you have some picture in your mind, or if you have some diagram, if you have some way to connect with what the prompt is telling you, that will help you to get some sense of what is going on in the question. So, even at the beginning when we drew this picture and we were looking at the tracheal tube and modeling it as a cylinder, it's useful then to think, oh, it's starting off at 1 centimeter. And then as you cough, this is going to contract, right? So even just drawing silly pictures and not very precise pictures like this can help you make sense of the problem. That's not something that I put as a step in these boxes. Step 0, make sense of the problem. But it helps, and it really helps to make sense of the problem at some point, hopefully initially. Great, thanks for watching.